Good morning, everyone. How is everyone? Good. Nothing like a can of Coke to start the morning off, is there? Lovely. It is impossible. What do those words conjure up in your mind? What emotions do they trigger? I'll tell you, for me, when I hear the words impossible, I see that as a challenge. If someone says it's impossible, I'm like, challenge accepted. You may well have heard me say, and I've definitely said in the past lots of time, there's no such word as impossible. I'm much more of a don't give me problems, give me solutions kind of guy. So given that, why would I pick the title of my session for this conference to be, It is Impossible to Calculate Wireless LAN Capacity? Well, maybe, it's a controversial topic. I thought it would get lots of votes, and, here I am. Or maybe it's because as I've got older and wiser, maybe just old and cynical, I've realized that some things are impossible. They really are impossible. So, let's, for example, take trying to lick your own elbow. I don't know if you've ever tried, but it's just impossible. And when you try, you look stupid doing so. Go on, you can all try. Okay, you don't want to look stupid, I get it. But you look stupid trying. Now, and it's because it's just impossible. Now I know what's going to happen. I'm going to finish this talk, and some of you are going to come up to me, and someone's going to come up to me and go, you say it's impossible to lick your elbow, but my sister's cousin twice removed, she can lick her elbow. And, I admit, I did my research on it, and, apparently this girl can lick her own elbow. Some people are just odd. So, okay, there's some people with exceedingly long tongues who can lick their own elbow. So maybe that wasn't the best example. Let's maybe pick another example. I'm just going to drink some more Coke. Take this Coke can. It is impossible for me to get any more Coke out of it now. It's empty, it's impossible. I can try, but I'm not going to get any more Coke out of it. That really is impossible. There's no use when it's Coke can. We can crush it, we can toss it in the trash. That is impossible. So some things are genuinely impossible in life. So what I want to propose today is that it's impossible to calculate wireless LAN capacity. So let's stop looking stupid trying to do it. Okay, I maybe need to say a bit more than it. I've still got another 50 minutes to go. But that's basically my talk. So let's look at some reasons why I think it's impossible. And I would like to introduce you to Stanley. Stanley is one of my friends. If you've not met Stanley before, then let me encourage you to go and check out the MIST wireless LAN design site. It's mist.com/design, where this is a completely free site by Juniper Networks, where you can be guided through a series of videos through the entire wireless LAN design process, which I have recorded. And you will meet Stanley and Misty, two characters who take us through the Wi-Fi design process. Now, please don't go there now, because it sort of upset me if you all started watching videos of me talking when I'm here live talking to you, but do go and check it out later on. But Stanley, you see, he is a wireless engineer, but as his name suggests, he's a bit of a tool. And he often comes across some difficult problems. So here is Stanley trying to do some capacity calculations. He has got a 90,000 seat stadium. So he goes, okay, 90,000 people. What do they have? Maybe 4 devices per person. They may have a watch, a laptop, a phone, a tablet. And what do they need to do? They need to support 4K video streams. So that's 4 times 90,000 times 4K video. And therefore I need 2 trillion access points. And then he's like going, oh, where am I going to install them all? And it's funny, it's a cartoon. But how often do we try and do capacity calculations like this? Where we come up with a number of users, we then times that number by some number of devices per person, which someone makes up. And then we work out what's the maximum amount of data they need. And then we times that by this number of devices we've got. And then we try and work out one AP has so much capacity, and we divide it by that, and then we get this magical number of APs we need. And can I tell you what happens nearly every single time you do that? You install too many access points. Nearly every time. And people end up installing too many access points. That's the problem with these capacity calculations. Let me take another cartoon picture of Stanley. Here he is overseeing an installation of one of his designs. And even his installation engineer is questioning as he's putting a grid of APs on the ceiling. Are you sure this is right? Now we laugh at it, but the idea from this cartoon is actually based on a real life experience I've had. I was once asked, just going back there, a customer of mine who, a retailer, was going to have a conference for all their store managers across the UK. They have about 800 stores, so 800 store managers coming to a conference. They normally used to use an external conference centre, but decided to use their own conference room for it, which could just about fit 800 seats in it. They were aware that currently, because they never used it for any big conferences, it had one AP in the middle of the room, lit up the whole room, but one AP not enough for 800 people. So they had someone internally do some capacity calculations. And they went, 800 people, and they said they had come up with the average person has 1.5 devices. Fair enough, so they said, okay, so that's 12,000 devices. They worked out a certain bandwidth that they thought each device needs, and they came up with a maximum bandwidth, they came up with throughput per AP, and they came up with a number of 38 access points for its room by doing a capacity calculation. And then they were getting the Cisco APs they went, it's high density, so we need these high density antennas, the big Cisco high density antennas, and literally their design that they showed me was literally, you looked at the ceiling above the seating bank of 800 seats, and it was just a grid of antennas about that far away from each other, in rows, covering, they created a new ceiling almost. Luckily for them, they tried to order it, and there was a delay on the antennas, and they weren't going to come for the conference. And that's the only reason they contacted me. And they said, we're just wondering, would this design work if we used integrated antennas? And I took one look at the design. I said, the design won't work if you use integrated antennas or external antennas. And they went, why? I said, you've got too many access points. And then they showed me their capacity calculation, and luckily I was able to create a more sensible design. But so this sort of thing happens, and it happens all the time. And it normally ends up leading to us putting in too many access points. That's one of the big problems. So I want to talk through some elements of that. Why is it wrong? Where do we go wrong with that calculation? And the first thing I want to mention is the number of devices important? Let's think of how many users, how many devices, let's times that by, let's times the number of devices by the number of users, and then we get this figure. And that's one of the reasons we often end up putting up too many APs, in my opinion. Because we end up somehow seeing the number of devices as a number of users. So if we say there's 4 devices per person, all of a sudden we have 4 times the number of users trying to access our network. Now, one of the problems is, and what you'll hear some people say is, well, one user can't use multiple devices at the same time. And there's some truth in that. You're not going to have someone, on their iPad, on their phone, and on their laptop all at the same time. People can use multiple devices at the same time, though. So if I'm a student in a student study room, I might have some music streaming to my phone, and I might be working on my laptop, accessing some files or doing some internet research. I've got 2 devices at the same time working. But if you think about that activity, I could be doing that on just a laptop. The music could be being streamed to the laptop and me doing that activity on the laptop. The devices, in terms of the amount of data I need as a user, doesn't really matter. What's important is how much throughput does that user need. Whether I do it across 1 device or 2 devices isn't so important. So, is the number of devices important? Well, sometimes it is. Let me tell you about when it is, first of all. I think the number of devices is important if you've got very high density environments you're designing for. So what am I talking about very high density? I'm talking about stadiums, large conference centres. And I'm talking about environments where there could be so many devices, we're in danger of not being able to get them all connected to the access points because we're going to max out the association capacity of the AP. That doesn't happen often, but in those type of environments, the only reason we need to know the number of devices is to make sure we can get them all connected. So if you look at a standard sort of enterprise AP radio, typically you're talking about 256 associations per radio. It varies a bit vendor to vendor, but that's an AP to AP, but you can get that number of associations. So what we need to make sure is we've got at least enough APs to get everyone connected and associated. That's the minimum number of APs we need. And typically you're going to work at about 50% the association capacity, because if you've got users roaming about, you want to leave headroom for users to roam. So you take a stadium, users tend to move from, at half time, they're going to move from the bowl to the concourse, and you're going to get a large number of users roaming at the same time. So you want to have some headroom. So in those environments, yes, we need to know the number of devices, because we need to make sure we can get them connected. But in terms of actually calculating capacity calculations, I think the number of users is far more important. And you want to know what bandwidth the user is going to take up and consume. How many devices I consume that over, I don't really mind. So yes, I can be streaming music on my phone and accessing some files on my laptop, but I could be doing that on my laptop, the music on my laptop and the files on my laptop. What I'm not going to do is stream music on my phone, my iPad, my laptop all at the same time, because I can only listen to one set of music at once. So it's more what activity users are going to take up is more important. So that's one place where people make a mistake with capacity. They start treating devices as users, and you end up getting way too much capacity that's needed. We should design to the customer's requirements. I believe it. If you go on the MITS Design website, you will hear me say it time and time again. This is really, really important. We design to requirements. We design to requirements. If you go on an ECSE course, you'll be taught design to requirements. But stupid requirements can result in stupid designs. Just because it's required doesn't mean we can design for it. Customers, and we know that, don't we? If people say, it's the requirement that you put the APs above the ceiling, that's a stupid requirement. It won't work. And when we come to capacity requirements, you can require more capacity than is available. We only have so much spectrum. We only have so many channels. We only have so much capacity in an RF spectrum. Once we hit that, that's it. There's no more capacity. You may require more, but I can't give you it. So, you can give me a requirement. We need to have 500 people in this room, and they all need to stream 4K video, 25 megabits per second, all at the same time, and that is my requirement. Great. I can't deliver it because we don't have that much capacity in the air. So it's important when we're working with requirements, we tune them to something that's actually sensible and can be delivered. Now, when I proposed this topic, if you read my little thing about what I was going to talk about, I said, if anybody wants to come and argue with me, they're welcome to come and argue on stage. And I thought, I wonder if anyone will bite. One person did. One person contacted me and said, I have a capacity calculation. That person is Ian there. Now, unfortunately, Ian couldn't make it to WLPC in the end. So he's not here to defend himself. So Ian, if you're watching this, I won. I did chat to Ian though, and I did say I would put a link to his blog, which is here on the screen. And in his blog, he talks about calculating capacity, particularly for auditoriums. And there's a few things I quite like in his blog. So I'm going to tell you what he says, because I think that's only fair, because he would have done if he was here, he would have come up and given his view on it. But what's interesting about his blog is he's not trying to answer the question, how many APs do I need? He doesn't try and do that at all. What he does is says, in my design, I've put this many APs in, how much capacity will that deliver? And it's sort of a reverse calculation. And that's why I say there's some things I like in there. So this is the figures from his, or some of the figures from his blog article. And he talks about designing for a conference in an auditorium with 500 people, and they're going to have laptops, and they're going to require 1 gigabit per hour because it's like a tech conference, so about 2 megabits per second. But what he says, and I think this is really interesting, he says, given the size of the room, 12 APs seems sensible. He doesn't say how he came up with that number, why 12 APs seems sensible, what made him, how he calculated 12 APs, and then he says, so we've got 12 dual 5 gig APs, this is the sort of throughput you're going to get, given a whole load of assumptions. Okay, these assumptions being 3/4 of all users being active at one time, 2 spatial stream devices, and he calculates the maximum throughput of an AP being 50% device speed. So now we're going to come back to this thing that how does he know 12 APs is the right number? I want to come back to that a little bit later on. Because ultimately he knows that because he's got experience at doing capacity design. Now, and he's come up with this figure that if you were using 20 meg channels, each user would have about 1.38 megabits per second. Okay, he's come up with that number. So, here's my question. If I went into a conference, this conference that had 500 people with laptops and smartphones, and I did a speed test, would I get 1.38 megabits per second? Most probably not. I would probably guess, actually, I would get more. Because I'm only going to get that if his particular scenario, he's basically said, you're going to get that if 3/4 of all users are all doing this 1 gigabit per hour, and they're using 2 spatial streams, and my throughput is roughly 50% of high speed. In that scenario, that's what you're going to get. How often is that scenario going to happen? Excuse me a minute. How often does that scenario occur? That's the question. Very, very rarely. In fact, is really you're going to have 3/4 of all users all doing 2 meg per second all at the same time, which is why I reckon you'll probably get more. In fact, I could go in there and maybe get 50 megabits per second. So it's almost like a worst case scenario, but really it's just in this one given scenario. You see, here's the problem. User behavior. His calculation can't calculate for user behavior. We don't, as human beings, behave in certain ways that we can predict. In fact, we're very, very unpredictable. Human beings do stupid things. Look, I've got proof. Now, I like climbing, and I like a beer, but I don't think I would ever do that. Human beings do stupid things, they really do. And therefore you can't predict what humans are going to do. So let's go back to our auditorium. And let's say we are trying to predict human behavior. Okay, we want to predict human behaviors. What do we know about humans nowadays? You know, people that live in our society, they absolutely love their mobile phones. You know, if there's ever a quiet moment, people are on the phones, you know. Most people walk around, you know, it's only that. If you look at people in our society today, there's 2 types of people, isn't there? There's Wi-Fi engineers, and there's the rest of the human range. Do you know how you tell the difference? Do you know how you know the difference? Everyone else looks down all the time, and Wi-Fi engineers are always looking up. So, people look at their phones. So let's say that's one thing we know about people. So there's a conference on, okay? What's the first thing people are going to do when the speaker stops talking? They're going to get out their phones and they're going to check their notifications, check their emails. You might think that sounds like a fair, logical thing to say. So therefore, we know at our conference centre when we're going to get the most people all trying to access the network at the same time is going to be when the person stops speaking. The point is, that's not true. It sounds logical, and I can see why someone would come to that conclusion and then try and build a network to meet that capacity. But when someone stops talking, what happens? Some people check to the person next to them about what's just been said. Some people are desperate for the bathroom and they're straight out the door. Other people are going out to where they're serving tea, coffee and refreshments because they want refreshments. And some people, yes, will pull their phones out. But not everyone. We're not robots that do things exactly at the same time. And that's why trying to account for human behavior in a capacity calculation is just impossible to do. It really is. So, here comes, I guess, the question is, how likely is it that people are going to transmit and try and access the wireless medium at the same time? And then we're going to get, how often do we get lots and lots of access? How utilised are our APs? That's one of the questions I want to look at. So to try and answer that question, I thought we'd look at, well, how long does it take to transmit a frame? Okay, let's go back down to a frame. Now, these images are from German's airtime calculator. I've put a link to it, which is quite a neat little tool if you've not seen it. But it allows you to try and calculate the amount of airtime that's going to be used up for a frame transmission. So the ones I've calculated here on this slide, I've picked 3 different packet sizes, and they're using MCX7 on a 20 meg channel single spatial stream, just as examples. And we're showing the time needed for the entire transmit opportunity. That's doing RTX, CTX data acknowledgement. So on this slide, if we're taking a look at it, at the beginning we've got a diff, that's an interframe space. There's then some sort of backoff, random backup to contention window. Then we have the physical layer header sent at a different speed. We've got an RTX, we've got a CIF, we've got then the CTX, a CIF, we've got our actual data, then we've got a CIF, and we've got the acknowledgement, or the block acknowledgement. And it's showing roughly how much time that would take up. Now, even looking at something like this, these numbers are not 100% accurate. So even though I'm going to use it to try and talk about capacity, even this isn't accurate. Why is this not 100% accurate? Well, first of all, it's assuming we're going to do a diff before the transmit opportunity. We could be using an arbitrary interframe space. It's got a contention window, which is a random backoff. Well, that's a random amount of time that we can predict. So I don't know how long that's going to be. If you were using WMM, then each access category, and I won't go into too much detail on this slide, but each access category, you have a different length interframe space, and you can have different backoff timers. So this time at the beginning of your transmit opportunity varies. But it's a reasonable guess, okay? On this slide, a reasonable guess. And as we can see on this slide, the smaller frame size, we got all done in about 400 microseconds, and the larger frame was around 550, maybe a bit more microseconds, okay? That's how long it takes to send a frame. So let's just say, so we can do some calculations based on this, let's just say an average frame size took about 550 microseconds to transmit. Okay? That's how long it takes to transmit a frame. In a second, we have 1 million microseconds. Therefore, in 1 second, frames that take, if it takes 550 microseconds, I can transmit 1,818 frames in a second. One. There you go. In that second, there was 1,818 frames that we could transmit. It's a lot, isn't it? It's a lot of frames in 1 second. How likely is it that two people are going to send frames at the same time within that second? If you click a link on a web page to open up a new web page, you know, a lot of web pages take maybe, 400 frames to transmit? And you see it, don't you? You click links now, and it's pretty instantaneous, the new page loads up. But there's 400 frames that were transferred in microseconds. Even if I got two of you to click a link at the same time, right? And I went 3, 2, 1, go, what are the chances you do it at exactly, you make a request to the RF medium at the same time, do you think? Well, the average response time for a human being, I've got the figures here, is between 150 milliseconds and 300 milliseconds. That's roughly the average response time. Between that time, you could transmit 272 frames. So if I went ready, steady, go now, what would be the chance that you both hit at exactly the same time and request the medium at the same time? Yeah, 1 in 270. It's quite low, but it could happen, but it's quite low. So hopefully you're starting to get a bit of a flavour, but let's work through, I also want to work through a little example here, because, okay, that's okay with 2 people, but what if there's 100 people in an open office area? And what are people doing nowadays? They're all on Zoom calls, they're all doing voice, they're all doing latency-sensitive applications. And you're saying, Peter, they're just sending packets all the time, voice packets every 20 milliseconds. What about that type of scenario? Well, let's take voice as an example. So, on this slide, I show a G711 frame. G711 encodec, that encodes 20 milliseconds of voice every single packet. So if I'm on a voice call, I have to transmit a packet every 20 milliseconds, and I have to receive one every 20 milliseconds. Voice frames are quite small. To encode 20 milliseconds of voice, it takes 160 bytes. 160 bytes of G711 payload. Then you've got your 12 bytes of RTP header, you've got 8-byte UDP header, you've got 20-byte IP header, and if you're looking at the full Mac frame, you've got about 20 bytes for your 802.11 Mac header. So when I took the length of a voice frame and I put it into the airtime calculator using MCS7, one spatial stream, on a 20 meg channel, I found out it takes about 400 microseconds to transmit. That's how long it takes to transmit a voice frame, given that we're using RTS, CTS, and acknowledgement. Okay? So, what does that mean? Well, we've got to transmit one of those every 20 milliseconds and receive one every 20 milliseconds in a voice call. So, that would mean if it took 400 microseconds, what that would mean is I could transmit within a 20 millisecond period 50 voice frames. That's what I'm showing at the bottom of this slide. 50 voice frames in a 20 millisecond period. So that would be, because I need two, one sending, one receiving for a voice call, that would be 25 voice calls. So if I had no other traffic on my AP, and my voice clients were one spatial stream using MCS7 in a 20 meg channel, I could get 25 voice calls on an AP. That's the max I could get. Which, if you look at some vendor statistics for voice calls, if you have absolutely no data, that's roughly what people say, about 25 voice calls per AP. So it works out. But here's the interesting thing I want to show you. MCS7, 20 meg channel, one spatial stream, the max data rate is 72.2 megabits per second. That's what it is. If we were using Ian's calculation of saying the max throughput for an AP is 50% the data rate, we would have 50% of that, which would be 36.1 megabits per second. So the max data rate of an AP MCS7, one spatial stream, should be, if you do that 50% rule, should be about 36.1 megabits per second. Well, let's do a bit of math on what we just worked out with these voice frames. Okay? So if we can transmit 50 voice frames in 20 milliseconds, it means in a second, I can transmit 2,500 voice frames. And if you work that out, 2,500 voice frames, that would give you 3.2 megabits of G711 data. Or if you want to include the RTP header, the UDP header, and the IP header, it would give you about 4 megabits per second of IP data throughput. So the maximum throughput, if all I've got is voice calls, is actually 4 megabits per second. Nowhere near this 36.1. Why is that? It's because we're using really small packets. And the smaller the packet size, the less throughput you're going to get. You see, the throughput statistic of using 50% is assuming you're doing like a iPerf test to it, sending the biggest frames possible, UDP frames with as much data as you can constantly all the time to it. And yes, then you may get about 50% of data rate. But when you're using small packets, your capacity of your AP drops. So what is the total capacity of an AP? Well, it depends on the makeup of your packets and sizes. If just, for example, just to sort of make this point a bit further, if we said, okay, we've only got 20 voice calls, then that would leave me 4 milliseconds every 20 milliseconds for data. And if in that 4 milliseconds I decided to fill it with the biggest data frames I could, 15, say, 100 byte data packets, my overall capacity throughput of my AP would go up to about 6 megabits per second. Still quite short, isn't it? Because I've still got most of my time spent with voice calls, with small packets. So hopefully you get the picture that capacity is really, really hard to calculate. There's so many different variables. Even working out the capacity of an AP is difficult because it depends on the makeup of the frames that are being sent. It's really, really hard. Now, So, okay, I'm sort of saying that capacity is hard to calculate. And I'm also trying you to realise that the amount of throughput you actually need is often a lot less than you calculate. I've already said we put too many APs in. We often think we need a lot more capacity than we actually need. I've had conversations, it's the same argument that I've had with people when they've gone, we really need multi-gig on the new APs. And I'm like, you don't. You're not using anything at the moment. But okay, it's easy for me to say, but can I prove it? Show me the data, Peter, to back up what you're saying. Wouldn't it be great if I had some data that I could show you this morning? Well, yes. Before we get there, that's a little tease. I want to talk about one more thing. I like giving little teasers. Wouldn't it be great if I had some data? Well, maybe I do. But before we get there, one more thing. I want to come back to Ian for a second. I said that Ian said about 12 APs is the right number for this room. And he didn't say how he knew that. He didn't say where he got that from. That was just mentioned one line in his blog article. Well, let me tell you how he knew that. He knew that because Ian's designed multiple conference centres, multiple church buildings, multiple auditoriums, and he's learned how to design a network for capacity. And you might go, well, that's okay, but that doesn't help me out. The point is, Wi-Fi design is as much of an art as it is a science. And if we treat it just like a science, we want a mathematical calculation to design capacity. And we're going to go down that route, and we're going to look stupid doing so. Okay? We don't want to look stupid. But there is an art form to designing Wi-Fi. And how do you get good at art? You practice. If you paint, you don't just walk up one day, put a canvas in and draw a masterpiece, do you? You go to art class, you practice and you practice and you practice. Now, I had a friend who played the violin. And he was, when I was at school, one of my best friends, and he was one of the best violinists in the whole of the UK. He was the first violinist for the National Youth Orchestra. And I went to watch him in a concert once, and he was playing a solo, a really complex solo. It sounded brilliant, and there he was, and halfway through his solo, a string snapped. Do you know what he did? He didn't stop, he kept playing, and he transposed all the notes from that strings onto other notes and just carried on with it seamlessly. And I was like, how do you do that? Now, you may know the science of how to transpose a note from one string to another, but to do that live in a concert with hundreds of people watching you, that is art. And the reason he could do that was because he practiced 4 to 5 hours every day without missing a day for years. He was dedicated to his art. That's why, how do you get better at designing capacity? You do it, and you learn from it. Wireless and design is as much of an art, and we need to practice that art. We need to get better at it. We can't always just rely on some sort of numbers we can punch into a calculator. Okay, I said I may have some data for you. I've got some data. I've got what I think is some very good data, and I want to thank Juniper Mist for this data. This is their data, it's not my data, but they've allowed me to present it to you today. I want to thank Wes Purvitz in particular for helping me with this and working with me on getting this data. We have got nearly 1 billion data points here. And what we're looking at, the Ethernet throughput of access points, and we have got the Ethernet throughput for every minute, for every missed AP, for a 7-day period in July. And that is nearly 1 billion data points. So what does it tell us, and what have we learned from it? Well, let me show you, I'm going to show you 3 charts. There's loads of data and analysis we can do with this data, but I'm going to explain what we've got here. The way we organise the data, because it was a lot of data, and I say we, probably mainly Wes, I won't take all the credit here, but it's organised in groups. So APs, first of all, by what was the bandwidth of the AP? So we're looking at 20 megahertz APs that were running 20 meg channels first. I'll show you 40 megs next. And then group the data into APs that had 1 client connected, APs that had 1 to 10 clients connected, 10 to 20, 20 to 30, all the way to 100 plus. So the data's been grouped based on how many clients were connected to the AP. Then, what we've done is taken all the data points in those categories and ordered them from highest throughput to lowest, the data points. And then what we're showing you on this chart is the percentage. So if we took, say, the bottom 95% of all data points in that category, what was the top throughput? Meaning that all the others were below that, of all those data points. Does that make sense? So let's just have a look what we're saying. So what we're saying is, and I'm only showing you on this, the 95% of all data points and 99.9% of all data points. They're the 2 percentages we're looking at. But if you took 95% of all data points we got, regardless of how many users were connected, they're all below the 50 megabits per second line. So 95% of all data points for a 20 meg channel were less than 50 megabits per second. In fact, some of them are, you can see the line, it's quite well below, it's below 20 megabits per second. 95% of the time, the throughput across all mixed APs never went, looking every single minute, never went above 50 megabits per second. I don't know whether that surprises you or not. But it didn't. Just to put a bit of context behind it, we haven't shown it on here, but if you went to the 80%, it never went above 10 megabits per second. So for 80% of the time, you could have had a 10 meg Ethernet cable plugged into your AP. This is across all missed APs every minute for an entire week. Now, if we go to 99.9% of all data points, so we're only excluding the very top 0.1%, we did get the odd, in that top percent, the odd time you did see an Ethernet port maxed out, did happen, but we're talking 0.1% of all these nearly billion data points. If we look at that, the throughput still never goes above 250 megabits per second as the highest throughput that we saw on any of those data points. In fact, when you get loads and loads of users connected, it's not even above 150 meg. Because the more users you have, the more collisions you're going to have, the more congested the spaces, you're not going to get as much throughput through. There's actually a sweet spot, as you said, to look at this data of maxing out an AP, you get a sort of around sort of often, I don't know, 30 to 40 users tends to be where you get the most throughput. It's interesting. There's lots of things you can get from this data when you study it, but interesting, isn't it? So we're not really maxing out our APs much at all. Now, you use a wider channel, we've got more throughput, so, okay, you're only showing 20 meg, Peter, what about 40 meg? Well, here's 40 megabits. 95% of the time, it did go a little bit in the sort of peak zone around 40 to 50 users, but most of the time, 95% of the time, we were never more than 100 megabits per second. So for 95% of the time, you can just have a 100 meg Ethernet with a 40 meg channel plugged into your AP. You don't need a gig. This is real numbers, real data. And then we see, if we go to 99.9% of the time, we never go above 500. Sometimes we're below 400 meg. If we just take that sort of data points, over 95%. Interesting data. Here's the data, both graphs on one graph, just so you can see the green lines are 20 meg and the blue lines are 40 megabits per second. So, do we need multi-gig on APs? No. We very rarely, 0.01% of the time, need a gig connection. I hope you're finding this interesting. If you have questions on this data, do come and chat to me, chat to Wes, he's here as well. I'm sure he'll be more than happy to chat a bit more about it with you. What I don't want to do, though, at this conference is leave you all in a bit of a low. We've just started the conference, and Peter's got on stage and said it's impossible to calculate wireless length capacity. Just give up, don't bother trying anymore. Unless you've got lots of experience, you can do it. I don't want to leave you on a low. I want to finish on a little bit of a high. So I want to finish with a bit of magic, if that's okay. Because magic is an art form as well. And you see, when we do art, we can achieve great things. So, one thing I said was, I'm just going to go back to my can of Coke example. Just going to scrub around in a bin. So, I've got my can of Coke. Now, this can of Coke, as I said to you, is useless. And it's impossible to be used for anything. But the question is with a bit of magic, and a little bit of finesse, what can we do with this can of Coke? Could we somehow restore it to its former glory? Could we make this can of Coke somehow... Now, I don't know if I can hold it near my microphone, and you might hear something. The bending of metal. As this can of Coke, hopefully, you might, especially people at the front of my bed here, there's a few little slivers of metal that we're getting. And what I'm trying to achieve, if we can, if it will allow me to, it's been very slow about it, but I'm trying to restore it to its former glory. Which isn't really, which I think I've punctured a hole in the can, which is not helping very well when I bent it. But anyway, but what's happening, as it's filling up with Coke, instead of punching out the holes, it's just leaking. But it is actually filling up with Coke, believe it or not, which only leaves me one thing to do, and that is fix the hole in the top. So if we mend the hole, we should be able to open the can again and pour out another thing of Coke. And that's all because I wanted to end by saying, sometimes the impossible is possible. Thank you very much.